Hello, everyone, and welcome. I am Zoe, a member of the ICCT communications team. Thank you so much for attending today's webinar. This webinar is being recorded, and we will send out the recording to all participants sometime next week. Everyone has their microphones on mute. If you have any questions, you can write them in the control panel in the questions box to the right of your screen. After the presentation, we will have a few minutes to answer questions from the audience. Today, we are going to talk about powering zero-emission trucks, U.S. infrastructure needs through 2030. Presented by Pierre-Louis Ragon. Pierre is an associate researcher on the HDV team, but before Pierre's presentation, I would like to introduce Ray Minjares, our Heavy Duty Vehicles Program Director at the ICCT, who will give some brief remarks. Take it away, Ray.
Thank you so much, Zoe. Welcome, everyone. Thank you for joining us for today's webinar. As Zoe said, I'm the director of the Heavy Duty Vehicles Program here at ICCT, based out of our San Francisco office. And I'm joined by my colleague, Pierre Ragon, who's in our Berlin office. And we will very briefly provide an update on a study that was just released yesterday that quantifies where, when, and how much infrastructure is needed to support the growing fleet of zero-emission trucks in the United States through 2030. I'm going to provide some brief context first for this study. I'll pass it over to Pierre, who will then walk through why we did this study, what the methods are, and what some of the key results are of the study. And then I'll conclude with some brief remarks on what are some of the options and solutions utilities and other energy providers have to delivering that infrastructure in a timely manner. We'll have time at the end for a few questions, but overall, I want to try to keep this webinar relatively brief. So we have some slides here that I expect you all can see. And I wanted to just first start with some international context. When we look across the globe, the US heavy-duty vehicle market is trending towards a greater number of zero-emission vehicles. Globally, as of 2021, there were an estimated 117,000 zero-emission heavy-duty vehicles, with China dominating the market, and that has been the trend for many years now. China is the world's leading market for zero-emission heavy-duty vehicles. That market is dominated today by buses. By our estimates, nearly 3/4 of the heavy-duty vehicles in China today are buses. But other road freight vehicles are growing in number, not only in China, but also in Europe, the United States, and other regions. From a kind of public policy perspective, these other key markets are advancing their policies to accelerate the uptake of zero-emission heavy-duty vehicles. So when we look at the Chinese context, their vehicle fleet growth has historically been driven very much by fiscal incentives and other government subsidies motivated by industrial policy. China is also deploying zero-emission vehicles to address its air pollution challenges. And so, for an example, it has a National Clean Diesel Action Plan. In its most recent revised version of that plan, it is targeting that 40% of new vehicles in 2025 be either zero emission and what they call new energy vehicles, or China 6, which is equivalent to today's Euro 6 standards, or the cleanest combustion engines that you can buy today in the US. In certain key regions, the government's goal is that 80% of all public buses, urban trucks, and refuse trucks be new energy. In other words, basically electric. In the European context, there is a proposed CO2 standard for heavy-duty vehicles, and that would require a 90% reduction in the standards by 2040. And that's in relation to the US, which has also just proposed a phase 3 greenhouse gas standard. It's that standard which will be the opportunity for the US market to really transition in a more accelerated way to zero emissions. The Inflation Reduction Act is one policy that the government, that the US government has really put into effect to stimulate the growth of zero emission heavy duty vehicles. And by ICCT's own estimates, in a study we published in January, approximately 44% of the heavy duty vehicle class 4 to 8 market in 2030, we expect would be zero emission. We expect that will be dominated by battery electric powertrains, with fuel cell vehicles being just a small percentage of the total ZEV market. And we just 2 weeks ago published a study showing the strong business case that exists for battery electric powertrains in the US. And we looked specifically at long haul tractors and worked with the actual utility rate schedules in 7 different states to really reflect a bottoms-up estimate of what the price of electricity is across those markets. And so from this perspective, we found that in this decade, long-haul battery electric tractors, we expect will achieve price parity and will be cheaper to own and operate than diesel. In comparison, we don't see that same dynamic for hydrogen fuel cell or hydrogen internal combustion engine vehicles. And we also see a strong advantage for battery electric tractors relative to hydrogen fuel cell. This is one way that we illustrate this. Effectively, so long as the price of green hydrogen is in the range of let's say $6 or greater per kilogram, we really don't see a market for hydrogen fuel cell. All of that would require much more expensive electricity or pretty dramatic innovations in the production and distribution costs for green hydrogen. And in various states where we did this analysis, we found that that TCO parity year could be as soon as 2027 in states like Florida, Texas, Illinois, and others. Slightly later in states like California that have higher electricity prices. So I'm going to pause there because that is the kind of context for our infrastructure study, which makes the point that this transition to zero emission is really going to be led by battery powertrains across all weight classes. And what that means is that for the US to realize the full potential of not only the zero emission transition and the public health benefits that come from that, but also the economic benefits that come from a vehicle powertrain that can actually be cheaper to operate than diesel is. It means that the timing and the availability of the infrastructure is crucial to realize that full potential. So for this reason, we have yesterday published a major study that really quantifies where, when, and how much charging infrastructure needs to be available to realize that potential. And it's at this point that I'd like to hand it over to my colleague Pierre, who's the lead author of our study, did a tremendous job with it, and is really one of our international experts on this topic. So with that, Pierre, I will hand it over to you. I'm controlling the slides, so you just tell me when to move to the next one.
Great. Thank you, Ray. Thanks for the introduction and for the very helpful context. So if we can go already to the next slide, please. I'd like to say a little bit about what motivated the study. And as Ray mentioned at the very start of the call, there's really 3 questions that we try to answer to know what are kind of the action items needed to ensure we can deploy infrastructure in a way that will support the transition to zero-emission vehicles in the US. The first question is where to locate charging infrastructure. And so for this, we based our modeling based on existing data on truck activity in the US. I'll touch a little bit more on this to identify really what are key areas to focus investments and to focus policy support. The second big question is, when does this charging infrastructure need to be ready? And as many of you know, projects to deploy charging infrastructure can involve relatively long lead times, and so it's crucial to know when this infrastructure will be needed. The third and kind of related question is, how much power will be needed at each of those locations, and that will also inform the scale of the grid upgrades if needed, and we'll also see later that grid upgrades are not always needed, but if they are, this question kind of addresses how much power will be required at each of the charging locations. So really, those are the areas that we try to tackle with this study. So Ray, you can go to the next slide. I'd like to, before jumping into results and conclusions, I'd like to say a little bit about our modeling methodology. And as I just mentioned, so our assessment is really based on data for flight activity. And as a matter of fact, it's based on publicly available data. So it's using the Federal Highway Administration's HPMS data. For those of you not familiar, HPMS is the Highway Performance Monitoring System. And it's probably the most comprehensive, publicly accessible data set on truck activity and truck flows in the US. So what we do is first, we derive some assumptions on zero-emission vehicle deployment between 2023 and 2030. For those of you most involved with the ICCT, you might be familiar with the roadmap model. Roadmap is an internal tool that we have that is able to model vehicle stocks for different powertrains based on historical data for vehicle sales as well as projections. So we use this tool and we use it with a scenario on ZEV deployment that is aligned with our projections of future market growth. So this is essentially based on, currently adopted policies in the US, namely California's Advanced Clean Truck and Advanced Clean Fleets rule, both in California and other states that have adopted those regulations, together with the incentives introduced by the Inflation Reduction Act. So this kind of sets our assumptions on zero-emission vehicle deployment, and we apply this to the existing databases for truck activity in the US that is taking, flows of diesel trucks as they are today, making projections on how the total amount of freight will increase, and then employing a share of electrification in line with our assumptions. With that, we're able to map the daily energy demand on the US road network, and you'll be able to see some fancy maps in a few slides. And we do this at two geographical scopes. The first one is at the county level. So we look at what is kind of the energy needs from medium and heavy duty vehicle charging in each county in the country. And we also look at the freight corridors of the National Highway Freight Network. With that, what we then do is we estimate infrastructure needs at the national level and subnational levels. To do this, we make some assumptions on fleet preferences. That includes, the relative share of different charging power levels and relative shares of depot versus public charging. So here, what we assume is that basically all trucks that are based off a depot would charge primarily overnight at their depots. Whatever extra energy cannot be met by overnight charging will need to come from opportunity charging, and public charging really would be mostly accommodating for charging needs of long haul trucks along those freight corridors. So based on that, what we're able to obtain those results really is threefold. The first is we estimate the size of charging hubs along key highways to satisfy the energy needs of long-haul trucks. So that's one. The second one is we look at the peak charging load from all medium and heavy-duty vehicle charging. So that really includes all trucks, both at depot and public locations. And it's a measure of how much energy will be drawn at a given time from the electrical grid in each county. And the final thing that we assess is the nameplate capacity. So that really means, what if like all chargers that are installed to satisfy those energy needs, what if they were all being used at the same time? And that gives you an idea of like how the distribution and transmission lines need to be sized to ensure that sufficient power is brought to the charging locations. So that gives you kind of an overview of our modeling methods. And a final step before jumping into results, Ray, if you can go to the next slide. I just want to give you a little bit more of an insight into what kind of level of ZEV penetration we're modeling based on this scenario that I described before, that Ray kind of described as well a few slides ago. So really what this graph is showing you is our projection of the stock of class 4 to 8 zero-emission medium and heavy-duty vehicles based on this scenario through 2030. And what we find is that by 2030, we expect at least 1.1 million zero-emission trucks and buses on the roads, which represent about 10% of the total vehicle stock. So that gives you an order of magnitude of the fleet we're talking about. So if we go to the next slide, the first finding is that 10 states will account for about 50% of the national charging needs. So we find that energy demand from medium and heavy duty vehicles will mainly concentrate in states that have adopted the ACT rules and California rules in general, as well as states with the largest industrial activity in the country. That includes Texas, Illinois, and Florida. Then what you see on the right, this table shows you energy needs and vehicle activity for ACT states only. The reason why we're focusing on this is those states, have, among all states in the country, the strongest policy support to ensure that the economic opportunities that are brought by IRA incentives, between others, are actually realizing, and that we're actually seeing this level of zero-emission vehicle penetration brought to the market. Important to note, Texas and California alone will account for a combined 19% of energy needs in the country. So those states are really kind of key, and those are priority areas for infrastructure deployment. Now within those states, charging needs will concentrate in a few counties. And if we go to the next slide, please. Here you can see two maps that show you the county level daily energy consumption in megawatt hours per day in 2025 on the left and 2030 on the right. The labels that you see there identify the 10 counties with the highest energy consumption in both years. Now, what we find from this analysis is that the growth in energy demand will concentrate in key zones for freight. That includes big ports, industrial zones, and freight corridors that connect them. So if we go to the next slides, what we find is that 1% of counties with the highest energy consumption account for 15% of national energy needs. So you can see that from the state, we've refined this to county level and identified really what are the key counties on which to focus infrastructure deployment. The table you see here shows the top 10 in terms of energy demand, what we estimate to be the peak charging loads to match this energy demand, as well as the number of chargers required and the nameplate capacity represented by all those chargers for the 10 counties. As you can see from this table, most of them here are in California and Texas, and more generally, the counties are located in Southern California, the Texas Triangle around Dallas, Houston, and Phoenix, Salt Lake City, Chicago, Illinois. And what doesn't really show up in this analysis is also all the area in the Northwest around New York City, Boston, and Philadelphia. As you might have noticed from the maps in the previous slide, those areas have counties that cover less areas. So basically the absolute energy needs are lower, but if we then look at energy per unit area, the 6 of the top 8 counties are actually around, are the counties that contain New York City. So this is another area that doesn't show up in this part of the analysis, but that is also key for infrastructure deployment in the short term. Now, what does that mean in terms of infrastructure deployment? First, if we look at like the energy that this will draw from the general energy system in the US. We estimate that daily MHDVs in 2030 will draw about 140,000 megawatt hours from the energy system. This is about 1% of the total electric retail sales in 2021, according to data that we found on the Energy Information Administration's website. So really, this is a relatively small increase. It's not insignificant, but it's manageable on the power generation and power transmission side. Where things might become a little bit more challenging is on distribution capacity. And as you can see on the far right column of the chart, we have nameplate capacities that are relatively high for the top counties, so about 1,100 for LA County, for example. What that means is, early planning and management of existing and future capacity really will be key to ensure that infrastructure can be deployed at the right pace. Now, the same way we went from states to counties, we could also identify within those counties a few areas, basically the areas where fleets congregate, that will see the highest charging loads and the highest nameplate capacity. So this is not something that we pursued in this study, but within those counties, so for example, areas like the Port of Long Beach in LA County, or Ontario, California, or Newark, New Jersey, those are areas that are that we know congregate a lot of fleets and will see the highest loads within those countries. So that's kind of like one of the key outcomes of this bit of analysis. Now, if we go to the next slide, so charging depots will be key to ensure that trucks can charge overnight. But long-haul trucks don't really return to a depot on a daily basis, and those will mainly rely on public charging hubs. And what we find is that setting targets for charging station deployment along key freight corridors on the National Highway Freight Network can accommodate up to 85% of the charging needs of long-haul trucks by 2030. So the map you see on the left shows you those NHFN corridors together with our projections of energy consumption on those corridors. What we did in this bit of analysis is we assumed that charging hubs for MHDVs will be deployed every 50 miles along the NHFN. This is in line with the designation criteria for alternative fuel corridors that receive funding for infrastructure deployment. So we took this 50-mile distance assumption. This is the metric that is similar, if some of you are familiar with the European AFIR regulation, the Alternative Fuels Infrastructure Regulation, which actually sets binding targets for member states to deploy charging hubs of a certain size every 60 to 100 kilometers on key freight corridors in Europe. So this is kind of a similar approach that we're taking, looking at key freight networks in the US and saying what would be the required size of those charging hubs. One more thing that we're doing is because we recognize that freight activity might not be at the same level on all of those freight corridors, even though they already represent a subset of high priority corridors. We further divide this into 4 categories that represent the amount of traffic flow those corridors can expect. So those are really the 4 rows of that table you can see on the right. And what we find is that as a national average by 2025, charging hubs would need to have an installed capacity of around 900 kilowatts per station, and that by 2030 will increase more than tenfold to reach about 10 megawatts per charging hub. Ranging from slightly under 3 megawatts per hub for the lowest traffic band to up to 22 megawatts for the highest traffic band. So really those, are numbers that can seem significant. So from this, really, we have kind of 2 main recommendations. So the first one is that targeting investments and policy supports to those key locations can help really deploy the network of charging infrastructure needed to support this transition to battery electric vehicles. And the second that I will then let Ray expand on a little bit more is there are a number of solutions and options that exist today already and that need to be enabled in the future really to manage the grid capacity and make sure that this area of grid capacity that is such a concern for many players really isn't an issue to infrastructure deployment. So with that, I'll hand it back to Ray to talk us through some of those opportunities and options.
Thank you very much, Pierre. Just to conclude really on this presentation, I'm just going to wrap up with this final slide, because for all of the needs that Pierre and the team have quantified, there needs to be actions, right, to provide the necessary infrastructure. And those are actions that utilities, electric utilities, will be responsible for. So as we developed this analysis, we wanted to be sure that we captured what specific actions utilities and other energy providers can take, both to meet the immediate needs and also to plan for the future needs that will continue to grow at an accelerated rate. So we start with 2 key principles. The first is maximizing the use of existing grid capacity. That available grid capacity varies utility by utility and even within a given service area, block by block. So it really is the utilities themselves that know where that grid capacity exists, and specifically their distribution engineers. So important and time-sensitive conversations need to happen with the distribution planning teams at your local utility. In addition to maximizing that existing grid capacity, there is naturally going to need to be a growth in the capacity to satisfy future needs. So we start with these two key principles. And based on those two key principles, we've broken out the set of actions really in three different categories based on, let's say, least process-oriented to most process-oriented, requiring, potentially new policy at a state and potentially federal level. So at least with those actions that do not require any regulatory approval, meaning a utility does not have to open a docket or does not have to seek, specific authorization from its Public Utilities Commission. There are actions that utilities can take, such as rebalancing feeder loads, using what's called non-firm distribution capacity, likely on a temporary basis, but effectively every utility has a buffer in its available distribution capacity that it maintains really for safety reasons and to ensure reliability of the grid. So utilities naturally need to keep that buffer, but there are certain controls that they can utilize to tap into that buffer on a temporary basis while the permanent capacity is actually installed. So there's that idea. There's also the use of technologies like dynamic line rating. And of course, solutions that exist behind the meter, meaning solutions that the project applicants can deploy themselves, like smart charging. And finally, solutions that really open up opportunities for public-private partnership here. So solutions where a project applicant can bring their own financing, can bring even their own design and construction of the grid capacity in those instances where the utility doesn't have the resources or the capacity to meet the timeline that the applicant wishes to follow. These are solutions that we think has a lot of potential to bring in private investment and also provide greater certainty to the timeline of the projects themselves. But it really is up to the utilities and the project applicants to agree on that type of partnership. There are other actions we've identified here that require some level of regulatory consent and approval. These don't necessarily require a formal decision, but really are more necessary to keep regulators informed. So this includes explicitly including transportation load forecasts into distribution system planning. Also, solutions that could allow third parties to submit applications on behalf of their customers, many of whom don't have the staff capacity, the knowledge, or the experience to follow the process that every utility might have, each of which might be a different process, right? So, so that's what that would entail. We finally, and this is not a comprehensive list, so these are just a few highlighted ideas. The report has a longer list of ideas, but there is the idea of authorizing the pre-construction of the necessary grid distribution infrastructure in what we call no regret freight zones and corridors. So we know where trucks go. There is very high resolution data, both public and private, that is accessible to utilities. So we know where the vehicles are going. The ICT's work is showing what the needs are, and they really are concentrated in these ports, industrial zones, warehousing areas, and freight corridors. So, it sort of begs the question, why not go ahead and plan for and at least create the necessary conditions to absorb the growth in zero-emission trucking in those specific areas. And finally, this idea of steering connections to high voltage transmission lines, given that when we're looking at electric truck depots, especially along high traffic interstates, according to ICCT's work here, we're showing that some of the largest electric truck depots in 2030 may need 22 megawatt capacity. So aligning the installation of those near, high transmission lines and really allowing the direct connection to those can significantly reduce the planning burden and the construction burden and the cost burden, really, of these types of high capacity needs. So that's the simple summary here of solutions that we're highlighting today. But like I said, the report has an extensive discussion of a wider range of solutions that are available. And we think and hope that this report calls attention to solutions that perhaps are not being utilized currently, that certainly are in the control of utilities and other energy providers to deliver, and that really can accelerate the delivery of those interconnections that fleets are looking for today. So that brings us to the end of our presentation. I did want us to just take a few minutes here for those of you that are interested in just a couple of questions that have come forward. Thanks very much to those who've been submitting questions, and we have time for just a few. As Pierre was talking, I noted a few down, and Pierre, I'm going to put you on the spot here because I think you're probably better positioned than I am to answer some of these, but I think we can do this together. So first, I wanted to start with a very basic question on the capacity of the power grid to meet these demands, these energy demands. So the question is, will the US power grid be able to handle the power demands of trucks? So could you speak to what we know about that?
Sure. Well, I think first, maybe I want to reiterate the message that in terms of power generation and power transmission, we think that heavy-duty vehicles will, only increase the requirements by a marginal amount. Now, in terms of distribution capacity, I think it's a matter of early planning, early engagement to make sure that the distribution capacity is built on time. And I think it's much more a matter of timing than a matter of whether it's feasible or not. So I think, Ray talked to a lot of options that exist, but at the end of the day, it's also down to, individual fleets to engage with their local utilities to know really what's their particular situation and what they can expect, because as a research organization, there's only so much we can do. So it's really down to individual case-by-case projects, and then focusing on areas where it's feasible first, and then ramping up as the market develops.
And I think there was a statement in one of the earlier slides that showed our estimate that in 2030, the projected energy demands of the zero-emission fleet would be equivalent to about 1% of the retail electricity sales that exist in 2021. So as a percentage of total electricity demand, this zero-emission truck fleet will be relatively small. I mean, 1% is a pretty small number. But as you rightly pointed out, Pierre, and I think as I've come to realize in this work, the challenge isn't about, do we have enough electricity available that's being generated? The challenge really is about getting that generation of electricity in the right places, right? And in the right volumes, because we're talking here about, you gave the example of, the average electric truck depot in 2030, we're estimating would need to have a capacity of about 10 megawatts, right? That's about the size of a reasonably sized data center, right? And here we're talking about every 50 miles. So I think that's the way I'm starting to think about this challenge. It's as if you're dropping in a data center, you know, along every interstate every 50 miles. And in those really industrial areas where you have dense urban warehousing, every warehouse might be equal to a data center. So that's really the challenge. It's about serving that concentration of energy demand in these particular locations where it's not easy to move a warehouse, right? I mean, these are places that have been built up over decades, right, in our urban centers. And so the challenge for utilities is in traversing that existing network of infrastructure and really expanding its capacity in order to meet those needs in those specific places. There's another question here just on what some of our assumptions were, Pierre. And so I wondered if you could answer a question regarding what assumptions we're making regarding the capacity of the charging equipment itself. So if you can just explain again for folks, just what are we assuming the size of the chargers actually are, and what, you know, and then say a little bit about peak load and how we're generating those estimates. And maybe I can go back to the slide that you had here, which I think captures some of this.
Right. So quickly, because we're nearing the end of this. So overnight chargers, depending on truck segments, and we're modeling different truck segments individually based on the move segmentation of MHDVs. Overnight chargers would be specified anywhere between 50 kilowatts and 150 kilowatts. This is the maximum rated power of the charger. It doesn't mean that the fleets will be drawing the maximum power from each charger. So especially fleets that don't have too many operational constraints might be drawing power at a lower level. But this is what we estimate will be the size of overnight chargers at depots. Fast chargers would be CCS standards. That would be capped at 350 kilowatts. And ultra fast chargers would be megawatt chargers. Could be anywhere from 1 to like several megawatts. And then in this study, we assume around 2 megawatts to be the standard across the country. So aggregating, you know, those chargers with their respective power levels, this is how we get to the nameplate capacity. And as I mentioned before, this gives you an indication of like the size of the distribution system that needs to be in place to accommodate those charging needs. The peak charging load is what we estimate that that fleets would be drawing from the grid at any given time, and this is informed by typical charging load profiles that we obtain from complementary data sets, as well as our assumption of daily energy consumption on the first column here. So this isn't directly linked to the size of the chargers, but more to the energy needed by the trucks themselves.
Thanks for that, Pierre. So I think we are out of time. I want to thank everyone for submitting your questions, and apologies for those whose questions we weren't able to answer. Many of you asked whether you can get the slides. So the slides will be posted on the ICT events page where you registered for this webinar. So that will happen as soon as possible, likely today. So you can look for the slides there. This webinar is being recorded, so for any colleagues of yours who did not have a chance to attend, you will be able to find a link to the recording on that same events webpage. And for those who are interested in the data that we generated, which included estimates of the daily energy needs of electric trucks by state, as well as by county, and for county scale estimates, peak load, and nameplate capacity load. We have that data all posted already on the website where you can download the same report. So all of that information is on the ICT website, and I invite you to download that. And please reach out to us with any questions. I'll just post this last slide if you would like to follow up either with me or with Pierre, and we'd be happy to take those questions and continue the discussion. So thanks again for joining us today. I think with that, I will hand it back to Zoe, if that makes sense, Zoe, and you can.
Yes, certainly. Thank you, Ray. Thank you, Pierre. What a wonderful presentation. You summed up everything that I was going to say. Yes, please visit our website under the events section. You'll see the event page, and that's where our presentation slides will be posted. So we'll see you there. Great. Thanks, everyone.
Thank you.
Bye.